So we're back for, I think it's the fourth installment on your equilibrium PowerPoint notes via vodcast for AP Chemistry. And it's a short concept that we're going to study right now, a short segment for the concept of something called the reaction quotient. It's kind of cool because it's easy to calculate. It's just the same thing as the equilibrium constant, but basically you're punching in numbers for a system that is not at equilibrium. And all you need to do is to take the given initial concentrations, put them into the same exact kind of expression that you would do for a Kc or Keq, and look at the size of the number that you get when you're done. You'll compare it to the equilibrium constant, and that comparison of the two numbers will tell you which way your equilibrium is being driven to shift. To the right, favoring products; to the left, favoring reactants, or not shifting at all. So let's take a look at that last situation. If you do these calculations and come up with a reaction quotient, or Q, equal to your given equilibrium constant, you're at equilibrium. Done. If you do the number crunching and you find out you have a large Q, the way you interpret that, since the equilibrium expression is the same way we calculate the Q, the numbers on the numerator are products, the numbers on the denominator are reactant. So the only way you can get a number greater than the equilibrium constant is if you have too large of amount of product on the numerator of your calculation. So if you have too much product, it's like the equilibrium system senses that there's too much product and goes, ooh, there's too much product. I better hurry up and go back and shift more to the left to try to come back into equilibrium. So if Q is greater than, if Q is greater than the KQ or KC, your equilibrium will be driving to the left. I think you can figure out the last one. If you calculate a Q where there is too much reactant, then the equilibrium will be shifting to the right. Here's why. Reactants are on the denominator. If they are on the denominator, then that makes your number for the calculated Q too small. And so basically the reaction senses, ooh, I have too much reactant, not enough product. I better hurry up and turn this reactant back into product. I'm going to shift my equilibrium and drive to the right. Now all that's kind of gibberish until you look at an actual problem. So here's our favorite. You always see this one: hydrogen and iodine make hydrogen iodide, all the time. They give you the equilibrium constant, that is 50.5. This time, however, as they give you the moles of product and reactants, hydrogen and iodine, be careful because now it's in a 2-liter container. So when you do these calculations, the first step that you need to do is to change the moles in 2 liters into a molarity. Well, that's easy to do. It's a dividing problem. So now we have initial concentrations of the hydrogen iodide, the hydrogen, and the iodine. I write a Q expression exactly the same way as a KEQ. And so I have hydrogen iodide squared, the concentration of it, over the product of hydrogen times iodine concentration in the denominator. You take the values for initial concentration that were given to you in the problem, don't forget to square the hydrogen iodide, and you get a number. And we're done almost, except we have to do the last thing. You compare your equilibrium constant to the value of the Q that you just calculated. In this case, 1.3 is smaller than 50.5. So that means that we'll have to drive to the right to try to make more product, and the concentrations of hydrogen and iodine will be decreasing as we push to the right to try to make more product, and that will then influence the direction of your equilibrium. So that's how we use the reaction quotient to predict the direction of approach to equilibrium, and it's very easy to calculate. Let's stop there and we'll pick up on the Le Chatelier's principle in the last mini vodcast.